Okay. Hello, everyone who may watch this video. Today, our team will discuss our approach to predicting Airbnb rental prices using machine learning model. Our team members are Jiayu Kang, Tinghao Meng, and Zeqi Wang. So our goal for this project was to develop a highly accurate regression model that minimizes the root mean square error, or RMSE, which was the key evaluation metric for the Kaggle computation. The challenge was to take a dataset with various listing attributes and predict the expected rental prices as accurate as possible. We started with a dataset containing information on Airbnb listing, including their location, room type, number of reviews, availability, and host details. Since the test data set did not include actual prices, our task was to train a model on the available data and generate predictions and aligned as close as possible with real-world pricing patterns. To achieve this, we tested three different machine learning models. The first model we used was random forest, which is an ensemble learning technique that builds multiple decision trees and average their results to make predictions more stable. The second model was LetJBM, a gradient boosting algorithm, which is optimized for speed and performance. And the third model, XGBoost, is also a gradient boosting algorithm known for its highly accuracy and efficiency in structured data tasks. Initially, our model performed reasonably well, but we noticed that uh, they varied significantly in terms of how well they fit the data. Random forest appeared to be overfitting, meaning it performed exceptionally well on training data, but struggled on validation data. For LightGBM, on the other hand, showed signs of underfitting, which meant it was not fully capturing the complexity of the data, while XGBoost provided a moderate balance, meaning it was neither too simple nor excessively complex, but still had room for improvement. This led us to refine our approach by making improvements in feature selection, hyperparameter tuning, and outlier detection. Based on our result, we continued optimizing all three models, but the XGBoost emerged as the most balanced in terms of fit, making it our final choice for submission. Now I will hand it over to my teammate who will explain the specific improvements we made to enhance model performance.
Thank you, Tinghao. Now I will explain how we improve our model accuracy and reduce RMSE by processing data, including categorical feature and optimizing model performance. The first step was handle missing value, and a view per month column had missing value, which we replaced with the zero, since missing value likely meant this had never been reviewed. This approach kept the data constant without change the overall pattern. And next, we convert the categorical feature into numerical value so we model could process them. We use one hot encoding for neighborhood group, neighborhood, and the room type, which created the separate binary column for each category. To avoid mismatched feature, we also made sure that test data had the same structure as the training data set. Next page, please. After preparing the data, we trained the random forest, XGBoost, and the LightGBM, and compared the performance using the RMSE. We fine-tuned the XGBoost and the LightGBM, adjust setting like linear rate, max depth, and the number levels to improve the accuracy and prevent the overfitting. And next page, please. Once training was complete, we generated the prediction and visualizing the distribution of predict price using a histogram. Most predict price was between $0 and $500, which aligned with the real Airbnb pricing trend. A few higher predictions suggest that model identify naturalists without overestimating their price. After evaluating the model, we found that XGB boost perform best. Random forest overfit the training dataset means it's memorizing pattern, but did not generating well, and IGBM underfit failed to full capture pricing trade. And XGB boost provided a strong balance, makes it the best model for submission. To confirm our finding, we analyze learning curve to check if our model was underfitting, overfitting, or well-fitted. And now I will hand it to my teammate who can explain why we access the model fit and reliability.
Okay, thank you, Zeqi. Now I will discuss how we assess whether our model was underfitting, overfitting, or well-fitted. One of the most effective ways to analyze model performance is by using learning curves, which compare training error with validation error. Ideally, both errors should decrease as more training data is used and should be eventually coverage as the reasonable point. If a model is overfitting, it will have a very low training error by a high validation error, meaning that it's memorized the training data but struggles to generalize to the new data. On the other hand, if a model is underfitting, both training and validation errors will remain high, which means the model is too simple to capture meaningful patterns in the data. When we analyzed our learning curves, we found the random forest has very low training error by a much higher validation error, which confirmed that it was overfitting. On the other hand, light GBM showed high curves for both training and validation sets, suggesting that it was underfitting. This means that while light GBM was computationally efficient, it was not extracting enough information from the data to make highly accurate predictions. HGB Boost has the most balanced learning curve, with training and validation errors that were close to each other while remaining relatively low. This indicated that the SGB Boost was neither underfitting or overfitting, making it the best performing model in terms of the generalization. To further validate our results, we examined a scatter plot comparing actual and predicted price. The red dashed line represents the perfect predictions, meaning that any point directly on this line had an exact match between the predicted and actual values. Most of our predictions were clustered near this line, which confirmed that our model was making reasonably accurate estimates. However, we did observe some outliers, particularly lightings with extremely high actual prices that our modeling underestimate. This suggests that while our model performed well on average, it still struggled with the predicting very high-end listings. Overall, based on our learning curve analysis and validation results, we determined that SGB Boost was the best fit for the dataset, as it avoids both underfitting and exercise overfitting while maintaining competitive accuracy. Thank you for listening, and that will be all for today.